Thank you so much for the kind introduction. So my name is Visarute Pinrod, and also my colleagues Robin Ying. We are from Cornell University, and today we talk about PZT sensor and for near zero power sensor nodes. So first, we will give an introduction that you probably heard so many times today. And next, we will talk about how we solve the problem. We use PCT sensor technology to make a set of zero power sensors. And Robin will continue on explaining about his CMOS chip classifier and give a conclusion. So unentered ground sensors is a sensor that you may want to put in a rural area and to monitor interesting event. For example, in this photo, you may want to put a sensor close to a petroleum pipeline and detect when the car drive past by, and you may don't want to detect when there are, for example, bison walk past by and hit the sensor. So the goal, we want to minimize false alarm and we want to maximize the detection rate. And there are already a commercial version of this sensor available. Our project is funded by DARPA N0 program. So the idea is we will make a completely passive zero power sensors that use the energy from incoming signal itself and then feed the output of the signal into near zero power classifier chip. And we aim to consume power less than 10 nanowatts. And after that, that chip will send an output trigger to wake up any commercial sensor that you can design for the application. And our detection goal is we want to detect generator, car, or truck. For comparison with the available commercial model, if the event happen, for example, if the car drive past by all the time, 100% of the time, the high power hungry commercial sensor part will be awake all the time. So we are not focused on that. We are focused on the rare event that, for example, if the event occurred at less than 0.1% of the time in one of the model commercial available is consume 31 milliwatt. And if we use a 2 AA battery to power this system, the battery lifetime will be 15 days. But if we can decrease the power consumption down to 10 nanowatt, battery lifetime will be extended to 3 years. So this is our goal. Okay, and next, how do we build zero power sensors? We use a laser micromachining process. First, we start with a PCT substrate, which is a piezoelectric material, and it's a bulk PCT with electrode, silver electrode on top and bottom. And we use laser micromachine to etch through the substrate to define a mechanical structure. And then we use the same laser, but less repetition to remove only the top silver to define electrode. And by doing this, we can make a simplest structure, which is a PZT Lateral Bimorph. It consists of a PZT in the middle and bottom electrode that we are grounded, and top two electrode for sensing. The advantage is that this process is very fast. It takes 4 hours from after we finish design until we finish fabricate the device. The disadvantage is that the feature size is quite big. We get a feature size of 150 microns. So it results in overall sensor size is 2.5 centimeter by 2.5 centimeter. And the output voltage, so if you just consider a simple model, the output voltage will be proportional to the displacement of the tip. We have more rigorous model in our paper and also a few papers that we cite. So I will not talk about that here. And in order to make sensors, for accelerometer, if you just attach a proof mass to the tip of the cantilever, it will be sensitive to acceleration in the x-axis, but it also will be sensitive to the out-of-plane rotation. So in order to cancel out the out-of-plane rotation, we can add more sensing cantilever, and we can use the electrode combination as shown. So we will connect all the plus electrode together and all the minus electrode together and cancel out the rotation. And we do the COMSOL simulation to confirm the size of the tensile or compressive stress. And we also see that the stress in the bimorph is higher close to the anchor. So we can add a cutler in the electrode to only sense where there are high stress. So we fabricate the device and we calibrate it on a shaker table, and we get a flat band sensitivity of 0.1 volt per G. Next sensor is a magnetometer. So for permanent magnet, if you put permanent magnet parallel to the field, the force on the permanent magnet will be proportional to the gradient of the field, which it cannot measure a spatially constant magnetic field. But on the other hand, if you put it perpendicular to the field, it will have a torque, and this is linearly proportional to the magnetic field. So we decide to use this to make sensors. So if you just attach one permanent magnet to the cantilever, it will sensitive to the x-axis magnetic field, but it also sensitive to x-axis acceleration and also rotation. So we add another cantilever to cancel out the x-axis acceleration and use the electrode combination as shown. But in order to cancel out the rotation as well, we need two sets of the magnet. So we put a magnet in opposite direction and then use the electrode combination as shown to cancel out all the acceleration and leave only magnetic field. So again, we fabricate the device and we put it in a Helmholtz coil to calibrate, and we get flat band sensitivity of 31 millivolt per Gauss. And next sensor is microphone. So we use laser micro machine to make a glass vane, and then we attach glass vane to a PZT cantilever, and then this will act as a both microphone and accelerometer. So we have two sets of the these, and one of them is exposed to the hole of the box to act like a microphone, and another one is like get blocked to be a reference, and we can connect it to cancel out acceleration. And then we 3D printed box, and then for housing the microphone and all the sensors. And we calibrate the microphone and get a sensitivity of 4 millivolt per Pascal. And next, Robin will talk about the CMOS chip for classification.
So given this large suite of sensors and the different voltages that are coming out of it, we want to then make sense of this to produce a digital pulse which will correspond to the detection of a generator. How do we get from A to B? That's the question here. And so we noticed some key properties about our output voltages. And one of the most important things that poses a challenge is that these signals vary rapidly with regard to time, as well as they have really large differences in the amplitudes that come out, somewhere between 1 and 100 millivolts. So with these considerations in mind, then, we realized that our CMOS signal processing and classifier circuit must have 4 main criteria. First, we are given a design constraint by the program to have 10 nanowatts, and we have 2 sort of sub-blocks, and so each can consume about 5 nanowatts. This means, in particular, for the classifier circuit, that the main thing that needs to happen is rectification, because there's no other way to process these fast-varying signals. Additionally, we want to scale amplitude so that there's a meaningful comparison between these orders of magnitude difference voltage signals coming from our sensors. And of course, low power again, we do not have gain, so we have to use capacitive dividers, which is actually attenuating our signals. Also, we've recognized in some of our signal processing math that we want to be able to combine signals and look at correlation as well as other sorts of coupling between the different modes of sensing to form an interesting feature vector. And so again, low power, we use a capacitive combiner. And lastly, one of the requirements is to sort of have a trade-off between our probability of detection and our false alarm rate. And we implement this with a 6-bit active mirror, which I'll talk more about on the next slide. So given that we already have our suite of sensors and we've generated some sort of feature vector using this capacitive scale and combine, then we generate voltages, which will drive the gates of these, our main device FETs, which will generate a current that will have sort of proportional to the square of the gate voltage. And those currents will combine, go into this tunable load, and generate the voltage sum signal here. In the event that we're interested in performing some form of subtraction, which opens up our feature vector space exponentially, N1 minus and N2 minus will generate currents, which are then mirrored around and can subtract from some signal. If there's more questions about this, we can talk more about it later. But now I'll talk about how we integrate our suite of sensors with the CMOS classifier and how we tested this. Most importantly, we ran 15-minute tests multiple times, and we call success 100% probability of detection of 5 triggers in a 15-minute period. And these happened randomly and were different on every run. Additionally, there can be no false alarms during this 15-minute window. To make things even more difficult is that we actually had a physical generator. We plopped it in the back of our campus where there was pedestrian traffic as well as vehicular traffic. If you notice in the very back of that picture, there's a fence that blew over. That happened while we were testing. And you'll see that actually shows up in some of our testing results. And on the generator sits our suite of sensors, some form of that capacitive combining and scaling, and then our CMOS classifier. So there are a number of interesting things here, but most notably, we ran across 8 different classifier chips, and each one had a different power consumption due to process variation affecting the leakage currents of each of the separate classifier chips. Note here that for a feature vector built of only a single sensor type, whether the accelerometer or the microphone, we were actually not able to successfully pass both the false alarm rate and the probability of detection. That's because for the accelerometer, as people were walking by, we would have false triggers. And then in the case of the microphone, with the wind, we got 10 plus false alarms just due to vibration coming right through that hole. But more interestingly is that when we combine these signals either independently or coupling them together and subtracting out different parts of the signals, which can be scaled with our capacitive combining and scaling, we were able to achieve a majority of different sets of feature vectors, which were able to distinguish the generator from being on or off with a false alarm rate of 0 and a probability of detection of 100%. So in conclusion, we have a process for PZT laser micromachining for rapid manufacturing of sensors, 4 hours. We have implemented 0 power accelerometer, magnetometer, microphone with orders of magnitude different output swings. And we've designed CMOS classifier chips consuming 2 to 5 nanowatts, capable of detecting the generator with 100% probability of detection and 0 false alarms in that same 15-minute window. And so moving forward, if we increase the sensitivity and actually have intentional variations across our sensors, which is easily enabled by our rapid manufacturing, and if we use more complex feature vectors that actually make use of correlation, then we can actually distinguish between generators, vehicles, ambient noise, all while maintaining 100% probability of detection with 0 false alarms and all under 10 nanowatts. So this is our team, and we want to acknowledge the DARPA N0 program, as well as Troy Olson, and of course CNF and CCMR, which are the nanofabrication facilities on campus.